we have a graph. So the structure is for the array. The representation of the graph is array. So for example, here it means the node 0 connected to 1 and 2. So for this node 0 connected to 1 and connected to 2. Here for node 1 it connected to 3, and for node 2 connected to 5, and for this is 3 connected to 0. You can see it is here. And for 4 it is connected to 5, and 5 there's didn't connect to anything. So for 5 there's no outgoing. Yeah, so there's no outgoing degrees. There's only ingoing. There's only in degree. There's no out degree. And for 6 there it is didn't connect it to any node. Yeah, what we need to return? We just need to return an array containing all the safe nodes. Now we need to understand what is the safe node. For understanding the safe node, we need to understand the terminal node first. Yeah, basically this question is about understand the description and then use the topological sort to solve the problem. So the terminal node is just like the node 6 and 5, for example. 6 didn't connect to anything, didn't go out, and 5 didn't connect to any node. So 5 and 6 are terminal node. And the node is a safe node if every possible path starting from that node leads to a terminal node. So we need to return all the safe node. So terminal node is a safe node. So this 5 and 6 are safe node, and this 4 connected to a terminal node. So this means that this 4 is a safe node. And for this 2, it's also only connected to a terminal node. So this 2 is also a safe node because this 2 and 4 didn't connect it to other node, which is a not terminal, only connected to terminal node for this 2 and 4. So this means why the result is 2, 4, 5, and 6. Yeah. So for example, if you check, for example, 3 connected to this 0, and 0 is not a terminal node. For example, this 2 connected to a terminal node, but 2 also connected to a node 0, which is not a terminal node. So this is why 2 connected to a terminal node. This is why 2 is the result. Yeah, but for others, for 0, it's connected to 1, and 1 connected to 3, and 3 connected to 0. So all those 0, 1, 3 are not terminal node. Yeah. Now let me analyze it in whiteboard because this drawing is even more confusing. It's not the it is not the drawing for analyze the topological sort problem. Normally we analyze the topological sort like this. So basically this is for 0 connected to 1 and connected to 2, and 2 connected to 5, and basically this whole structure is for analyzing the topological sort. Yeah, this is even better. Yeah, as you can see that the topological sort is like that, and the result is 6 because there's no node connected to 6, and this is a terminal node. For 5, it's also a terminal node because it is not connected to other node. Yeah, and for this 4, it only connected to a terminal node, and this is 4. And for this 2, it's only connected to a terminal node 5. It didn't connect to other node. Yeah, if you check other node 3, yeah, if you check other node for this one connected to 2. Yeah, if you check other node, for example, it is 1 connected to 2. 2 is a terminal node, but 1 also connected to 3. And 0 connected to 2. 2 is a terminal node, but 0 also connected to 1. Yeah, let me check because here there's something wrong. This is why I cannot use my drawing to analyze because let me just delete this one. Because the 3 connected to 0 and 1 connected to 3. Yeah, we have to make a drawing. Let me delete this 3. This is why it is more confusing here. Yeah, Now let me make the drawing even more clear. So 1 connected to 3, and this 3 connected to 0. It is like this. Yeah, as you can see, for 1, 3, 0, it is a loop. And inside the loop, there's a 1 connected to 2, 1 also connected to 3. So this means 1 is not a terminal node. And you can also check 0. 0 is not a terminal node. 0 connected to 2, also connected to 1. And for this 3, 3 connected to 3 connected to 0. Yeah. So this means 0, 1, 3 are not terminal node. Now we need to analyze how to find the result 2, 4, 5, and 6. And basically, if we find 6, that is okay, we can find it. And for 5, we can also find it because there's no outgoing edges. Yeah, only in degrees. There's no out degrees. But how can we find this 4? Because 4 only connected to 5. There's no edge. Yeah, there's no directed edge. So this means we cannot solve it like this way. Yeah, so we have to change the directions. After changing the directions, we can use the topological sort to solve the problem. Yeah, now let me change the directions. You're gonna understand it more easily. Yeah, let me just change the directions from here. So 5 will be connected to 2, 5 will be connected to 4, and I'm gonna also change the directions here and here. Yeah. Now the directions will be like this. 1 connected to 0, 2 connected to 0, and I forget actually for this 1, 2, 3. So this 1, 2 connected to 3. Now 3 connected to 1. And for this node, it will be like this. And here will be nothing. And 0 will be connected to 3. So after change these directions, we can solve it easily. Yeah, because we just need to check the integers. For 6, the integer is 0. We just put it inside our result. For 5, the integer is also 0. We just need to put it inside. Because here, the integers just means the out degrees from the beginning. Because we just reverse the directions. So this is important to solve this problem. And for this 4, because normally 5 and 4 have already put it inside the queue for the BFS with the topological sort. So now, if we already get the result of 6 and 5, now we are going to try to put it 4 inside. Can we put it inside? Yes, we can. Because this 5 is a terminal node, integer is 0. If we put it inside the queue, this 5 will be pop it out of the queue. If it pop out, so it will be, go to this node 4. If it go to this node 4, this degree will be disconnected. So the integer for this node 4 will become 0. Now, this 4 can also put it inside the queue. But can we put a 2 inside the queue? Yes, we can, because before the integer for 2 is 1. Now, while this 5 loops through traverse to 2, it also be decreased by 1 because this end will be disconnected. Yeah, this end will be disconnected. It will be decreased by 1. If it decreased by 1, the integer for this node 2 will also become 0. So the 2 will be also put it inside the result array. Now let's check if we can put others inside or not. Yeah. So can we put 0 inside as well? Yeah, if we put 0 inside, this is disconnected. Before, the integer is 2 because 1 is also connected to 0. Now the integer becomes 1. Yeah, it means we cannot put it inside. Now what should we do? If we didn't put this inside the queue, it means all others cannot put inside the queue. So whatever is not put inside the queue is only 6, 5, 2, and 4. So this means the result is 2, 4, 5, and 6. Because up to here, you cannot put 0 inside the queue. If you cannot put it inside, you cannot even put 1 and 3 inside anymore. Because the topological sort, the tree structure just goes to this 0 node. It cannot go anymore. And even it goes to 0 node, you cannot put 0 inside the queue. Yeah. Now let's write the code. Actually, the code is much easier. The hard part is about analyzing this topological sort structure. Yeah. Now let me try to write the template code for topological sort. Only the difference from the standard template is we're gonna reverse the directions. So we're gonna prepare the in degrees. If you gonna use the out degree, it will not work. Yeah, because for the out degree, you cannot use the graph traversal to find all the node. You only need to reverse the ends. Then you can find 6, 5, 2, and 4. If the direction is like 4 to 5, how can you find 4? Because 4 pointed to 5, not 5 pointed to 4. This is why we have to reverse the ends. Now let me do some preparations for the graph. It will be default dict. Inside it will be a list, and the in degree gonna be 0 times the length of the graph. Now we are going to loop through the graph. So the graph is an array. So for I not in enumerate graph. Yeah, here because we need to reverse for node inside the node. So we are basically checking every node inside this node array with this I. This I means the index, means the node 0 to node 1 and 2. Basically, we are doing these operations. So for the graph, up to now, the graph we need to put it inside is node or I. Yeah, before we put it inside I. Now we need to change the directions. It means we need to put the node inside with append I. And what about the in degrees? So in degree, let's check the drawings here. So for example, so 0 to 1 and 2. So 0 to 1 and 2. So what about the in degree? So in degree is the index. Yeah, because now the root is 1 or root is 2 connect, and the array put inside is 0. Now for the in degree, so for this 0, it is 2. Yeah. Yeah. And the in degree with I, let me check. So yeah, so the in degree should be plus 1. Yeah, because the in degree for this node 0, it becomes 2. Yeah, from the beginning, the 1 and 2 is still 0, but for this 0, it becomes 2. So this is y. So for the in degree I should plus 1. Yeah, if we put one node in, if we find one node, so the in degree should be plus 1. If we find 2 nodes, so the in degree would be plus 2, because here we find 2 nodes. So this is just preparations. After the preparations, we don't need to do anything for this question. We just need to finish the template code. So actually, this is the hard part. Yeah, we just need to reverse the graph. And now we prepare our template code. So code should be equal to deq and I for I will enumerate the graph. We need to check the value. If this v equal to 0, we're gonna put it inside the queue. Now we just need to traverse the queue. So the node should equal to queue dot pop left. And now we are going to check the neighbors. So for neighbor in the node, so the neighbors of the node, we are going to check the neighbors. So if the in degree of this neighbor, first of all, the in degree of the neighbors should be -1. Yeah, because we find a neighbor for our topological sort, for example, 5 to 4. Yeah, let me go back to the drawing. So for example, 5 to 4. If 5 connected to 4, and 5 already inside the queue, and its in degree for 5 is 0. When it traverses to 4, we are sure that the 5 is a terminal node, and we're gonna decrease the in degree for the node 4 because 5 connected to 4 directly, and for the terminal node connected 4, it doesn't matter, so we can directly decrease the value by 1. If it is 0, the integrate of 4 becomes 0. We can put it inside the queue. Now the integrate of this neighbor would minus 1. Now let me copy the integrate of neighbors for the if tag. So if it is 0, we can put it inside the queue dot append this neighbor. Now we just need to return the result. We need to sort the result. This is why I needed to use a sorted result, because as you can see here, the result should be sorted. Now let's check in ascending order. So this is sorted in ascending order. Now let me run it to check if it really works. So I didn't prepare the result array. It is an empty array. Now let me run it again to check. Oh, something wrong. I didn't put it inside my result. So basically I just needed to put the node inside my result. So result.append this node. Because for this node, the integrate is always be 0. I wanted to put the zeros, put the node with the integrate of 0 inside my result. Now let me run it again to check if it works. It's empty. Yeah, it's empty. Now let me check the queue, print out the queue. Well, yeah, I did something wrong because it is not graph, it is G. So currently G is my graph. This graph is just another representation because I transferred this graph to an adjacency list. I'm gonna use the adjacency list as this G as my graph. Now let me run it to check if it works. So there's only 4 inside the queue. It is not right. I for IB enumerated Z. It's not Z. It's not Z. Yeah, I just write the wrong template. It is the integrates. It is not the graph. I need to enumerate the integrates if this value is 0. Yeah, this is just something. Yeah, I made a mistake. It's not the graph or something else. It is the integrate. This variable. Yeah, I need to check the integrates if it is 0. Now, as you can see, it works. Now let me submit it to check if it can pass all the testing cases. After that, I will analyze the time complexity. As you can see, it works, and it's pretty fast. I still think, yeah, even it is 15%, it is still okay because it all depends on the environment. Yeah. Now let me analyze the time complexity. So for here, we basically used 2 for loops, as you can see. But here, it also told us, so the number of edges in the graph will be in the range of 1 to 4 times 10 to the power of 4. So it means the edges is not n squared. It is basically the same, the order of n. It is the number of vertices. So the vertices is 10 to the power of 4. So the edges is basically the same, 10 to the power of 4. Yeah. Now we just need to check how many edges inside. So for here, we enumerate the graph. And there are 2 for loops, but it is not n squared. Yeah. You may think it is n squared, but here it told us the edges inside the graph. And for this one, basically we are checking all the edges for these 2 for loops. So for the first one, we're just checking these vertices. Yeah. But for each vertices, how many edges it has in total. Yeah. So in total, how many? 4 times 10 to the power of 4. So basically, this time complexity is just 4 times 10 to the power of 4. This is why you can pass. Yeah, so basically this is ON. It is not ON squared. You need to understand that. This is not a dense graph. It is a sparse graph. For here, this is just for the integrals for the ON. N is the number of vertices. And let's check, let me delete here. Maybe I delete it and submit it. It will be even much faster. Yeah. And for here, it is ON. and this Q is also ON. Here is the thought n log n. So the final time complexity is n log n. Basically, it is 10 to the power of 4 times the log 10 to the power of 4. It is basically to the scale of 10 to the power of 5. That means why it is so fast. Now let me submit it again to check if it is faster, because I delete the print. If we print something, it will decrease the speed and memory. Yeah. Now as you can see, it is a little bit faster than before. Thank you for watching. If you think this is helpful, please like and subscribe.